Typically, when we think about something changing from one phase of matter to another, we think of it with heat. Okay, we heat something up, so its particles move faster and faster and faster. That means their kinetic energy is increasing. Okay, so on average, the kinetic energy represents the temperature. Okay, faster moving particles, higher kinetic energy. So overall, the average kinetic energy means a higher temperature. Okay, same goes for if we remove heat, particles move slower and slower and slower, and so the temperature drops as that kinetic energy drops. All right, so typically that's how we think of a phase of matter. But it's not just about that. It's also about how the particles space out, okay, which we kind of represent with potential energy. Okay, so as particles space out more and more and more, their potential energy gets higher as these attractive particles are trying to get farther from each other while they're still trying to, attract. Okay, whereas if they come closer and closer together, the potential energy drops as they kind of fall in line with those attractions and sort of stick to each other. All right, but if that spacing bit kind of is an important part of what phase of matter we're dealing with, a solid, a liquid, or a gas, then pressure actually has something to do with what we're dealing with. And maybe we should kind of think of it more often for what phase of matter we've got. Now, we typically kind of ignore pressure, how something pushes or forces on a sort of area, because really the only pressure we have being put on something in the lab is air. Air is constantly pushing on us. These little particles of nitrogen and oxygen, carbon dioxide and argon just kind of zipping around and bouncing off stuff. And we're so used to it we don't even notice it, unless you wave your arm around like an idiot like this. Okay. But it is there. There is pressure constantly on things. Okay? That pressure measures out to be 1 atmosphere. We creatively and cleverly came up with a pressure unit to describe the air pressure of our atmosphere. We measure it in atmospheres, and it just so happens to be that the pressure at kind of the surface of the Earth tends to be around 1 atmosphere pressure. Go figure. Okay. Now, if we change that pressure, we theoretically should be able to change something's phase of matter just as much as temperature can do so. So, for instance, in this syringe, I've got some hot water. Okay, it's not boiling hot, but it is hot. It's pretty darn warm. Okay, now I've squished most of the air out of this, so it should just be mostly water in here. So if I pull the plunger down, I should be giving this more room without something else filling the space. That should reduce the pressure on the liquid here. So when I do so, I start to see some bubbles form. See if I can get a better grip on it. I start to get the liquid to boil. Now, I haven't made the liquid hotter by doing this. I've just changed the boiling point. I've made it easier for the water to escape as a gas because I've reduced the pressure pushing down on it. Without air constantly forcing it together, well, now the particles can get away a little bit more easily. So that's all this is doing. I take something that already has some particles that are moving pretty fast, and I reduce the pressure, which gives them the ability to escape. Okay? Vice versa, if I push down on something, I add more pressure, I should be able to keep it more towards like the solid end of the phases of matter, okay, where I keep all the particles close together, even if they're moving really fast. If I keep increasing the pressure, I should kind of hold them in place and keep them stuck to each other, okay, or at least stuck near each other. Okay? And this is typically how most phases of matter work with temperature and pressure. As temperature increases, our particles kind of get more and more wild. They can get kind of more towards a gas. Okay? Whereas if we are putting on more pressure, we're keeping them closer and closer together, so they're kind of tending more towards a solid. And it's kind of a fight, a competition between those two, where we wind up. We use a phase diagram to figure out whether we are dealing with a a solid or a liquid or a gas at that pressure and temperature combination, and how we change from there as we change the pressure or as we change the temperature, or both. But there are some substances that act a little bit weirder. Okay, we sometimes call them non-Newtonian fluids because as we add pressure to those fluids, we end up seeing them change viscosity, which is a fancy way of saying how easily they flow. So, for instance, water flows pretty easily. Okay, so we'd say that has a low viscosity. Something like syrup has a high viscosity. It kind of flows slowly. It has a resistance to kind of flow and tumble over itself. Okay, so there are some substances that as we push on them, they change how viscous they are. Okay, we either call it shear thickening or shear thinning, depending on which way it goes. So things like ketchup and yogurt are shear thinning. As you shake them up and stir them around, they get more fluidy. So you might notice when you first open up like a cup of yogurt, it seems pretty like gelatinous. It kind of just is a big glop. But as you kind of stir in your fruit or just kind of start getting scoops out of it, it starts to kind of flow a little bit easier. Okay. On the other hand, we can have shear thickening stuff too, where as we put pressure on it and we get those particles to rub against each other, we have more friction. Okay, and as a result, it gets more viscous. Okay, that's what we're going to look at today. We're going to use a combination of water and cornstarch to make a non-Newtonian fluid. Okay, that is also just happens to be close enough to that barrier between the solid phase and the liquid phase that all it takes is some amount of pressure to make that change from one to the other. Okay? So to do this, we're going to take about 30 milliliters of water, okay, in a graduated cylinder. Okay? I'm going to add them into a beaker where I'm going to be combining these two things. Okay? Now, if you want this to have a color, you should probably add it in now. Otherwise, it's going to be hard when the cornstarch is in there. It gets all clumpy, and so it's hard to get it to mix. So I'm going to add in my food coloring now. I'm going to pick red if I can. Let's see if I can find where I put it. I might have to go searching for it. Give me a second. Okay, so I found my red food coloring. All I need is just 2 drops. Okay, or if you want, you can do 1 drop of 2 different colors if you want to mix them. Okay, so 2 drops. 1, 2. Swirl that up there. Very nice. Okay, and then I need to add in about 6 spoonfuls of cornstarch if you're using a spoon about this big. Open up my cornstarch. Nothing special about it. It's not lab grade or anything. It's just something you can buy at basically any grocery store. All right. 1, 2, 3, 4, 5, 6. Now your spoonfuls might be a little bit different than someone else's spoonfuls, so it might take some adjusting from here. Starting with about 30 milliliters of water and 6 spoonfuls of cornstarch should be pretty close, okay? But it might not be exactly what you're shooting for. We want it to be still liquidy, okay? It should still be able to flow, but it should be very thick. It's going to be like pancake batter, essentially. That's the way I kind of see it, okay? Now, because we are making a substance that is going to change viscosity as we mix it, in this case, it's going to feel thicker, it's going to feel more viscous, you should expect it to become very hard to stir this, okay? So you don't want to use your plastic spoon to try and mix this up because it's just going to break. We need something like this metal spatula or some other metal instrument to get in there and really stir this, okay? So even now, I'm already having a little bit of trouble trying to stir it. Now, a trick to this, since what's causing this to thicken up is the pressure that I'm putting on it, if we kind of go a little bit slower and a little more gently, then it actually is a little bit easier to stir. Okay, so if you're having trouble with this, just be patient with it and be gentle. Usually you can stir it pretty well. Okay, and this is about the consistency we're going to look for. Something like this. Okay, kind of like slime. I've got some on my laptop. There we go. Get that back in there. Okay, so something like this. Okay, so at first it doesn't seem much different than kind of your average everyday slime. We tend to call this stuff oobleck. in the industry, in the biz. Okay, and this stuff is pretty special because of how it acts as we change the pressure on it. Okay, so like I said, it does thicken up. Okay, but it even is more kind of a farther extent than that, than just like, oh, it just gets more viscous something. So what I'm going to do is I'm going to get some of this into my hand. I'm just going to like pour it out. Then we're going to kind of roll it. Okay, so I'm going to apply pressure to this. I'm going to roll it, push on it. Okay, and it's not leaking out from in between my hands. I can actually keep it pretty solid. Okay, until I let go of it, and then it starts running, and then I can push on it more. Okay, and then as long as I continue to put pressure on it, I can keep it in a little solid glob. So this substance, this oobleck, is basically riding the line between being a solid and the liquid. And we can freeze it into a solid, technically, okay, by putting pressure on it, okay? And as soon as we let go of that, it melts back into a liquid, which is pretty wild, okay? So this is a lot of, kind of opportunity to try stuff out and have fun with this. If you make this at home, it will dry out, okay, as you continue to mess with it, but that just means it's losing water. So if you want to kind of rehydrate it, okay, and get it to flow more again, you just need to add a little tiny bit of water. Don't go overboard. If you do, just add some more cornstarch to balance it out, and you should be good. Okay, so experiment with this and try this for yourself. Again, all you need is cornstarch and water, and if you want, a little bit of food coloring, and see how pressure affects solids, liquids, and gases, especially weird ones like this that we call non-Newtonian fluids, or specifically this guy we call oobleck.